Hello everybody, this is Dr. Christopher White, and today we're moving on to lecture number 13. So we're still in the Precambrian, but in this lecture we are going to be dealing with the Proterozoic eon, the third of the three eons of the Precambrian. So this particular lecture is going to be split into two, so it's going to be about an hour today, about an hour for this lecture, and the next lecture will probably also be about an hour. So alright, let's get moving. So the Proterozoic eon is a real monster. So it covers a period between about 2.5 billion years ago to 500 million years ago. So it's approximately 2 billion years in size. So like the Hadean and the Archean, Proterozoic rocks contain few macrofossils that would allow us to allow the correlation of units, very few fossils that would allow us to actually define boundaries within sequences of Proterozoic rocks. So, once again, just like the Hadean and the Archean, it's very difficult to separate the Proterozoic into distinct portions. However, although a substantial portion of the exposed Proterozoic rocks have undergone some degree of metamorphism and deformation, there are some areas of Proterozoic rock that are near pristine. So a good example of that is the Grand Canyon. And so if we look at the Grand Canyon, so at the bottom, towards the bottom of the Grand Canyon sequence of sediments, we have the Uincar group. And this is Proterozoic in age, and you can see from this picture, you can quite clearly make out these nice sedimentary layers. Essentially, it's a near pristine sequence of rocks, pretty much as the sediments were lithified. The group's been tilted slightly, but in the grand scale of things, they are pretty much untouched. So the Proterozoic differs from the Archean in that we actually have nice, relatively undeformed sequences of sedimentary rocks available to us, which we can study. So the change from the Archean to the Proterozoic is arbitrary. So as we discussed in the previous lecture, the boundary between the Archean and the Proterozoic was set at 2.5 billion years, and it was just set at that point pretty much because it was a relatively nice round number. However, the transition from the Archean to the Proterozoic is based on a few observations. So to start with, there's a change to more aerobic sediments. So we start seeing indications that the atmosphere is becoming more and more oxygen rich. We also see the appearance of facies associated with passive continental margins. So if you remember, during the Archean, the continents that were around were ringed by subduction zones. What we begin to see now is we begin to see some of those subduction zones stop, and the margins become passive. They become relatively geologically stable. We begin to see the appearance of epicontinental marine deposits. So these are essentially formed, these essentially can be, large bodies of fresh water or small bodies of salt water that form during higher sea levels. We also see a significant reduction in the rate of granite gneiss complex and greenstone belt formation. That also suggests there's less subduction going on, because if you remember, both of our models of greenstone belt formation required subduction. Either island arcs were crashing into each other, or we had back arcs forming behind island arcs in order to make greenstone belts. So once subduction becomes less common, essentially the rate of granite gneiss complex and greenstone belt formation slows down. So we see a change from the highly metamorphosed granite gneiss complexes and greenstone belts of the Archean to less metamorphosed to nearly completely unmetamorphosed rocks. So, in the whole, it's a lot easier to study Proterozoic rocks compared to Archean and Hadean rocks, because Proterozoic rocks are pretty common, and on the whole they are, geologically speaking, relatively fresh, relatively undamaged. So we see an unconformity at the transition from the Archean to the Proterozoic, and that's one of the things that's commonly used to approximately mark where the boundary falls when you have sequences of rocks. However, it's difficult to actually say if that boundary actually occurs at the transition from the Archean to the Proterozoic, or does that did that unconformity actually occur in the Archean, or did that unconformity actually occur slightly after the boundary in the Proterozoic? So yes, there is a boundary around the Archean Proterozoic transition. However, it's not actually datable. We think it falls somewhere around the boundary, but we're not really sure whether it's on this side, or directly on the boundary itself. So we can't really use it as a solid piece of dating evidence. It is a good guide, though. So here we can actually see this unconformity. So this is referred to as the Great Unconformity in the area that includes the Grand Canyon, and you can see it quite clearly here. So below us here we have a sequence of Archean rocks, so late Archean to early Proterozoic rocks. This is the Vishnu schist. This is a relatively high-grade metamorphic rock. You can actually see the layering in the rocks is near vertical. Okay. Above that, on the other hand, we have the Unkar group. Now these are essentially horizontally bedded Proterozoic sediments, relatively unmetamorphosed, relatively undeformed. So you can see here, this is where the contact between these two sequences occurs, and so this is going to be our angular unconformity, and this is the Great Unconformity that approximately marks the transition from the Archean into the Proterozoic, and I stress approximately. The problem with this unconformity is it is relatively common. It's found in lots of places, especially in North America, but it also occurs in Europe and South America. But the thing that needs to be remembered is that it's not universal. So we can't go to every area of the planet, and when we see the Archean Proterozoic transition, we won't always see this boundary. So we need to bear that in mind. So, as we also discussed in the previous lecture, they actually made an attempt in 2012 to redefine the boundaries in the Precambrian, and actually mark those boundaries out based on physical changes that we can see in the rock, or I should say physical or chemical changes that we can see in the rock. So, based on this process, the Archean Proterozoic boundary was actually set at 2.4 billion years ago. And it was based on the first appearance of glacial sediments. So, this is the first time we see, sediments related to glaciers actually appearing in the rock record. Once again, these sediments are relatively widespread, so they make a pretty good indicator of when you're moving from the Archean into the Proterozoic. However, just like this very, very large unconformity, they're not universal. You can't go to every location, we can't go to every location on the planet that shows the Archean Proterozoic transition, and you'll see glacial sediments. I mean, the picture above shows it quite nicely. We have these Archean high-grade metamorphic rocks down here. We have these nice horizontally bedded Proterozoic sandstones up here, and there's not a sign at all of any glacial sediments. So once again, these glacial sediments that can be used to define the transition from the Archean to the Proterozoic are not universal. So the Proterozoic marks a period of very substantial atmospheric change. So during the Proterozoic, we see photosynthetic bacteria increasing in abundance, and the atmosphere becomes a lot more oxygen rich. Now, the fact that we have all this oxygen suddenly being produced leads to the formation of extensive banded iron formations. And these banded iron formations are very, very important. Number one, from a scientific point of view, they tell us about the atmosphere becoming more and more oxygen rich. But they're also important from a mining point of view, because banded iron formations are the source of most of the world's mineable iron. So the Proterozoic marks the appearance of the first oxygen-dependent organisms and the development of the cell nucleus. So it's pretty much, we're relatively certain that we start seeing eukaryotic cells. Those are cells that have a nuclear membrane that can essentially packs the DNA into a tight space inside your cell. They make their first appearance in the Proterozoic. And this is very, very important, because as soon as you start taking the DNA and you start packaging it into a corner of the cell so it doesn't take up the entire interior of the cell, well, all of a sudden, once you do that, you have absolutely tons of room inside your cells. And so this means your cells have more room for organelles. So these are the parts of the cell that do very specific jobs. Things like chloroplasts and mitochondria, for instance. They're involved in energy generation, energy storage, those kind of processes. They help to make the cell more efficient. So all of a sudden, eukaryotic cells have all this extra room inside them. They can squeeze in more organelles, and all of a sudden, they become considerably more efficient. As we just touched on, the Proterozoic, is the first time in Earth history where we have known glacial events. And one of these glacial events could have actually been global. And we also see the formation of the first proven supercontinents during the Proterozoic. Alright, so what's happening with Laurentia in the Paleozoic? Oh, there's a mistake there. That should say Proterozoic. My mistake. I do apologise for that one. Don't know what was going through my head there. So the continent of Laurentia comprises a substantial portion of the central, northern and eastern United States and Canada. So Laurentia essentially equates to what is now modern-day North America. Included in Laurentia we also have Greenland, a portion of Scotland and possibly some parts of northern Europe. So essentially Laurentia is both North America plus a few extra things added on. So several landmasses which formed during the Archean collided in the early Proterozoic to form the core of Laurentia. So we're going to see Laurentia's formation. So the Proterozoic marks the period when North America begins its formation. So mass was added to the core of Laurentia through sediment deposition along its margins and repeated collisions and the accretion of island arcs along the core's eastern and southern boundaries. So what we're going to see is we're going to see lots and lots of very, very large orogenic events along particularly the southern and eastern sides of Laurentia, which are going to add considerable quantities of extra material onto the sides. Okay, so this is our starting point. So at the moment we don't actually have Laurentia. What we have are several provinces. So these provinces are essentially small pieces of continental crust. They are Archean in age, so they're older than 2.5 billion years. And as you can see, they are all separated from one another. Now, these pieces of crust are eventually going to start to move towards each other. So there's going to be subduction zones. The oceanic crust in between them is going to start being destroyed and subducted underneath these pieces of continental crust, and they are going to start moving towards each other. There are going to be collisions, and these collisions are going to bring all these pieces of crust together to form the core of Laurentia. Okay, so this is our starting position. So where do we go from here? So between 2.5 and 1.8 billion years ago, the Archean landmasses collided and sutured together to form the core of the Laurentian continent. So in geology, the term sutured means essentially two large pieces of rock sticking together and essentially locking themselves into each other. So they're very difficult to break apart. So the collisions of these pieces of crust resulted in several orogenies. I mean, if you look at some of these pieces of crust, let's say the Superior province here and the Hearn province here, they're pretty big pieces of crust. So when they hit each other, they are going to produce moderate to large size mountain ranges. So there are going to be several orogenic events associated with each of these pieces of crust banging into each other. Some of them will obviously be larger than others. So the collisions, as I say, resulted in several orogenies with widespread metamorphism, deformation, and the intrusion of plutons, so the intrusion of very, very large bodies of magma. So several key examples of these orogenies are the Tholian orogeny that occurred between 1.9 and 1.92 and 1.96 billion years ago, and that's when the Slave and the Ray cratons collide. So here's the Slave province up here. Here's the Ray province here. So the collision between the Slave and the Ray province is the Tholian orogeny, which occurs along here. Oh, got the wrong way there. Then we have the Trans-Hudson orogeny. That's between 1.82 and 1.84 billion years ago. And that's where the Superior, the Hearn, and the Wopmay cratons collide. So that's when the Hearn, which is here, the Superior, which is here, and the Wopmay province, which is here, all come towards each other. So the Superior goes this way, the Hearn comes this way, and the Wopmay comes this way, and of course there's a three-way collision. And then we have the Precambrian orogeny. That reaches its maximum at around 1.85 billion years ago. Now this isn't actually anything to do with these pieces of continental crust here, but it is quite an important event. So the Precambrian orogeny essentially is when we have several island arcs accreting onto the southern margin of the Superior province, and it results in a pretty significant mountain range forming along the southern and eastern margins of the Superior province. So those are just a few of the orogenies that take place during this period. So by 1.8 billion years ago, what's happened? Well, obviously we've had the Slave province, make contact with the Ray province over here. That's the Tholian orogeny. We've also had the Wopmay province, the Hearn province, and the Superior province come and make contact with each other, resulting in this pink area here. That's the Trans-Hudson orogeny. So that's a huge area of mountains. And as you can see, we also have several other juvenile orogens marked out here in the dark orange, and we have juvenile arcs, essentially island arcs, marked out here in the slightly lighter orange. So we've had a sequence of, these large pieces of crust bang into each other, and we've also had several pulses of island arcs also making contact with the margins of Laurentia, adding extra mass along those margins. So this essentially is the core of Laurentia, or what we would call now modern North America. So now I'm not sure whether you remember this all the way back from the plate tectonics lectures, but we're going to quickly touch on Wilson cycles again. So Wilson cycles named after Tuzo-Wilson, and Tuzo-Wilson was also rather famous in geology because he was the gentleman that actually managed to define what a transform plate boundary is and actually managed to show they existed. He also defined the idea of a hotspot like Hawaii. So Wilson cycles describe the sequence of events that occur when a new ocean basin forms. So a new ocean basin has to form through rifting. So a piece of continental crust has to split in two, and in the process of splitting in two, essentially the crust becomes thinned. The mantle underneath undergoes decompressional melting, producing basaltic magma that pours out onto the surface, producing essentially a basin, a depression, which fills with water, and so you end up with an ocean a bit like the Atlantic. So these ocean basins will eventually be destroyed by subduction, and we're going to see a sequence of diagrams in a second that's going to show you this process. Now, Wilson cycles can be relatively short, like the East African Rift Valley or the Red Sea. Essentially, they aren't going to last very long. Those two Wilson cycles will cease when Africa makes full contact with Europe. Or, on the other hand, some Wilson cycles can be rather long. So in the case of the Atlantic Ocean, it's been increasing in size for, since about 250 million years ago, and there's probably somewhere in the region of about another 50 to 100 million years of expansion to go before it starts to close up. So, Wilson cycles will obviously vary in length. And so this diagram here kind of demonstrates what's going on with a Wilson cycle. So in the case of a Wilson cycle, you're going to start off with a solid piece of continental crust here. Now, underneath this piece of continental crust, one of a couple of things can happen. Either you have convection cells coming up and round. Okay, you'll have one over here going this way. You'll have one over here going this way. And the fact that one goes this way and one comes this way means that the middle portion of this continent begins to become stretched, because this half of the continental crust is trying to go to the right, and this half of the continental crust is trying to go to the left, along with the convection cells. And so the central portion here begins to undergo extension. The other thing that can happen is if you get a sequence of very, very large mantle plumes coming up, they can get stuck underneath the continental crust, and these mantle plumes will obviously begin to cause the continental crust to dome up. That will stretch the continental crust, and eventually, the rock will fault, it will break. So once this area begins to become stressed, it begins to undergo the process of extension, well, the crust will fail, it will fault, and as the crust becomes extended in this area, it will become thinned. So as we've discussed in the past, when you thin the crust, the weight pushing down the pressure on this area of mantle underneath the thinning area is significantly reduced. That encourages mantle melting, and the mantle melting will lead to the formation of mafic magmas that will begin to rise to the surface and will begin to erupt into this rift valley here. So as these two pieces of continental crust move further and further away from each other, the crust in the middle becomes thinner and thinner and thinner, and that leads to more and more mafic magma production, and it eventually leads to the point where we have significant quantities of mafic magma being formed, and at that point we have the formation of new oceanic crust. Once we have new oceanic crust forming along a rift here, which runs down the centre along our essentially our mid-ocean ridge. Obviously, new crust is going to be made at the mid-ocean ridge, and these pieces of continental crust here and here are going to keep being pushed further and further away from each other. So the ocean basin in between them is going to keep getting larger and larger and larger. And this is the situation we have with the Atlantic right now. So you've got Europe over here, North America over here. We've got the Mid-Atlantic ridge here. So North America is going one way, Europe's going the other way, and the ocean in between them is getting larger and larger. Now, eventually what happens is a subduction zone will open up on one or both sides of this ocean basin, and the oceanic crust will start to subduct underneath the continental crust. So in this model down here, we can see the subduction zone opened up under the eastern continent, should I say the right continent. So the oceanic crust begins to subduct down underneath the continent here, and as we can see, the ocean basin is now getting smaller. The subduction zone will eventually subduct the spreading ridge, so that will be gone, so no more new oceanic crust will be made. And then we eventually get to the point where we have a collision. The two pieces of continental crust essentially come into contact with each other. That's going to result in a continent-continent collision, forming a mountain range. At this point, the two pieces of continental crust will suture to each other. They'll stick together. And then over time, the mountain range will be eroded away, and you'll be back to your original starting point. So these orogenies are very, very important, or should I say these Wilson cycles are very, very important, because number one, they lead to large-scale orogenies, but they also lead to the formation of very, very large ocean basins, full of crust, full of new juvenile crust, and full of sedimentary rocks. Okay, and so what we're going to see is as Laurentia is developing, we're going to see several of these very, very large Wilson cycles beginning, and we're going to see the resulting crust, new juvenile crust, and sediments on top of that juvenile crust essentially being incorporated onto the side of Laurentia as these ocean basins close up. Okay, so it's been 20 minutes, so this is a good time to pause the presentation, get up, have a walk around, get a glass of water, and come back in a few minutes, please. Okay, so, well, obviously, why was I going into Wilson cycles? Well, the important thing is that, as I said, we begin to see Wilson cycles starting and adding extra mass along the margins of Laurentia during this time period. So around 1.94 billion years ago, we see one of these ocean basins beginning to develop on the northwestern portion, along the northwestern portion of Laurentia, so up here. And you can actually see it marked out here. It's called the Wopmay orogeny. It's this kind of dark orange band right here, which continues down into here. So there's this orogeny that's going to occur down here. So there's going to be a mountain building event here related to the closure of one of these basins. So the interesting thing about the Wopmay orogeny is that the sequence consists of a suite of sedimentary rocks called a sandstone shale carbonate assemblage. Now, if you remember, these essentially sand, mud, and carbonate facies are what we tend to find on nice passive continental margins, like the east coast of the United States, essentially geologically inactive continental margins. So the appearance of these sandstone shell carbonate assemblages quite clearly show us that within the Wopmay sequence, as the basin opened up, essentially you had nice passive continental margins. So sediment was being deposited into and onto those passive continental margins, and then obviously those rocks were incorporated into the resulting orogeny, the resulting mountain range, as the basin closed up and the pieces of continental crust banged into each other. So these are some of the earliest passive deposits known. This is a very good indicator that we are moving from subduction-dominated margins of continents to more passive margins of continents. So we also see the same sequences being found in the rocks of the Pinokian orogeny. If you remember, the Pinokian orogeny was when we will have large quantities of volcanic arcs sticking themselves onto the southern and eastern sides of the Superior province down here. You can actually see the Pinokian orogeny down there. So this diagram kind of gives you some idea of, how the Wopmay orogeny actually started. Okay, so here is the western margin of Laurentia. So it's going to be this margin here. So essentially the edge of the slave province. And so the edge of the slave province is going to undergo extension. And so a piece of the slave province is going to essentially start moving westwards. So this is the slave province here. We're going to get some extension along the, in the western portion of the slave province. And so this over here is going to be the western edge of the slave province, and it's going to want to start to move this way, whilst the eastern portion of the slave province is going to remain where it is. And obviously, as this portion over here begins to move in this direction, the area between the two begins to be stretched. It undergoes extension. The crust begins to thin. Obviously, then we have a divergent plate boundary forming, with the mantle underneath melting, producing mafic magma that rises up to produce oceanic crust. So in between these, essentially these two pieces of the slave province, we now have an ocean basin forming, a little bit like the Atlantic. Probably a bit smaller though. So as you can see, both sides of the basin here are passive continental margins. So we have sediments being eroded from the high ground here, and here being deposited onto the passive continental margins here and here. And so we end up with these nice sandstone, mudstone, carbonate sequences, which show us quite clearly we had these nice passive margins. Now eventually, one side of this basin turned into a subduction zone, so the western side turned into a subduction zone, and the oceanic crust began to subduct underneath this piece of continental crust. This obviously means this piece of continental crust begins to move in an easterly direction. The basin in between gets smaller. Now that means all the sediments, well, essentially number one, we start forming volcanoes along this edge here, so it becomes an active margin, a bit like the west coast of South America. But also all of the sediments that have gathered along the passive margin here and on top of the oceanic crust here begin to become incorporated into the margin of this piece of continental crust right here. And you can see we end up with a sequence of volcanic rocks marked out here in grey and sediments marked out here in yellow. Obviously, over time, the two pieces of continental crust move closer and closer together, the basin's getting smaller and smaller. And eventually it gets to the point where the two pieces of continental crust make contact, and the volcanic rocks and the sedimentary rocks essentially are used to form the resulting mountain range, otherwise known as the Wopmay orogeny. So this is a nice, indicator that Wilson cycles have begun in the Proterozoic. It also shows us that passive continental margins are now becoming more common. And it also demonstrates that plate tectonics is beginning to operate in a fashion, in a way with which we are familiar. So let's keep moving. So we formed our continental core by around 1.84 billion years. So here it is. This is our continental core by about 1.84 billion years. We've gotten to this point here. So this is now one solid landmass. So what happens is Laurentia began to accrete new island arcs and crust along its eastern, southeastern and southern margins. And there were several key orogenies. Each of these orogenies was followed by a period of plutonism. So we had lots and lots of magma being placed into the crust as part of these orogenic events. Okay, so let's look at these four events. So we have the Wopmay orogeny. That's between 1.76 and 1.72 billion years. We have the Labradorian orogeny. That's 1.69 to 1.65 billion years. We have the opening of the Granite-Rhyolite province. That's 1.55 to 1.35 billion years. And we have the Grenville orogeny, 1.3 to 1 billion years. So the Grenville orogeny is important because it marks the formation of the supercontinent Rodinia. I missed out a H there. So the early stages of Rodinia formation began around 1.35 billion years ago, and it broke up around 0.78 billion years ago. So the rifting that occurs as Rodinia breaks up begins to form the Iapetus Ocean, which is going to become very, very important when we start talking about the Paleozoic tectonic situation with regards to North America. Okay. So the Wopmay and the Labradorian orogenies were the result of the accretion of juvenile crust. So juvenile crust, as the name suggests, means new crust, and most new crust is made at spreading ridges. But you need to remember this juvenile crust not only consists of essentially the oceanic crust, it also consists of the sediments that sit on top of it. So essentially both of these events, the Yavapai and the Matzo-Labradorian orogenies, are both Wilson cycles. So a basin is going to open up, then a basin is going to close up, and the resulting closure is going to form a mountain range, an orogeny. The Grenville orogeny is a continent-continent collision, a little bit like India smashing into Asia. It's a piece of continental crust coming out of nowhere and just whacking onto the side of Laurentia. Okay, so let's start off with the Yavapai orogeny. So the orogeny itself is marked out, or the area affected by the orogeny is marked out here in green, and the dark green colour represents the intrusive, so the magma that's in place after, well, as part of the orogeny. Okay, so we can see it occurs along the southern margin of Laurentia. So we can see what happens is a ocean basin begins to open up along the southern margin. And this ocean basin essentially is going to have a spreading ridge in the middle of it, creating new oceanic crust. And we begin to notice that essentially a subduction zone opens up along the southern margin of this basin. So the oceanic crust begins to subduct to the south. Okay, and so this means that essentially Laurentia is going to be pulled in a southerly direction towards this subduction zone here. And obviously the oceanic crust and the overlying sediments are going to, mostly the overlying sediments, are going to be scraped off, and they're going to result in the formation of a very, very large mountain range as the basin closes up. So that's going to be your Yavapai orogeny. And then obviously this sequence, this orogenic sequence then gets intruded by very, very large quantities of magma, typically granites. And so it's kind of a classic Wilson cycle sequence. So a basin opens up on the southern margin of Laurentia. It gets larger. Then eventually a subduction zone opens up along the southern side of this basin here. The oceanic crust subducts in a southerly direction, taking Laurentia with it. And as the oceanic crust is destroyed, the sediments get scraped off. And eventually, as Laurentia crashes into the subduction zone and the island arcs that essentially mark the edge of it, there's a bit of continental crust behind it. Essentially, you then end up with the formation of the Yavapai province. You get a lot of sedimentary material, a little bit of oceanic crust, and some island arcs all sticking themselves onto the southern margin of Laurentia, adding, I think you can quite clearly see, a significant quantity of new material onto the southern margin of Laurentia. So it grows pretty quickly. So the Yavapai orogeny is followed by the Matzo-Labradorian orogeny. So essentially exactly the same thing happens. So we have another ocean basin opening up. This time it goes along the entire eastern, southeastern and southern portion of Laurentia. It's a very, very large basin. So once again, just a standard Wilson cycle. An ocean basin opens up. So there's a spreading ridge in the middle of it, creating new oceanic crust. Obviously that oceanic crust once again gets covered in sediment. You have passive continental margins along here, passive continental margins on the other side of the basin down here, and then eventually a subduction zone opens up, and the oceanic crust begins to subduct. This time it's subducting in a northerly direction, so underneath Laurentia, and so the ocean basin begins to close up, and so once again we get the formation of a mountain range, which is mostly made of the passive marine sediment sequences and the sediment scraped off the subducting piece of oceanic crust, plus a few bits of oceanic crust. That forms the mountain range. And then within this mountain range, we get the intrusion of large quantities of mostly granite. So once again, you can see the opening and closure of one of these Wilson cycles has created a very, very large quantity of material, which has essentially stuck itself onto the southern, eastern and southeastern portions of Laurentia, once again increasing the size of the continent significantly. So then we have the formation of the Granite-Rhyolite province. Now you'll notice the word orogeny is missing. So something interesting happens when it comes to the Granite-Rhyolite province. It looks like the Granite-Rhyolite province is a partial Wilson cycle. So what seems to have happened is, if we go back to the Wilson cycle, we get to the point where we form an ocean basin, but on the whole it looks like this ocean basin never closed up. So it formed, but it never really got, the oceanic crust was never really subducted and destroyed. So essentially we just form an ocean basin, and this basin here begins to fill up with clastic and volcanic sediments. So it never actually collides, so this basin never closes up, there's never any collision, and therefore there's never the formation of a mountain range. There's never an orogeny. So this essentially seems to be a failed Wilson cycle. Then, as you can see here, we then have the final stage is the addition of this very dark orange to red material. This represents the Grenville orogeny, and this is when we have one large piece of continental crust here and a smaller piece of continental crust down here, the Llano province, which is part obviously of Texas, central Texas. These two pieces of continental crust make contact with the eastern and southern margins of Laurentia, and this is part of the formation of Rodinia. So in this case, what we have is we have material that's essentially coming from nowhere. This material wasn't part of Laurentia initially, there's no rifting involved. This essentially was just material that was once upon a time down here somewhere, and subduction meant that eventually it moved this way and made contact with Laurentia and stuck itself, sutured itself onto the side of the continent. And at this point, you'll quite clearly be able to see that essentially the entire core of North America has now been constructed. This essentially is, what North America is made from, the starting material. So let's just take a second to think about the Granite-Rhyolite province. So while the other three orogenies, so the Yavapai, the Matzo-Labradorian and the Grenville orogenies, resulted in a mountain range, hence the fact they're referred to as orogenies, the Granite-Rhyolite province did not. So we need to be able to explain, okay, why did this happen, or why, more importantly, why didn't an orogeny happen? So the Granite-Rhyolite province may well have been an incomplete Wilson cycle. Alternatively, it could have just been volcanics erupted onto the seafloor. Now, if a rift occurred, new oceanic crust was created. However, no substantial orogenic event occurred. So as I said, there was no closure of the basin that formed. So an ocean basin would have formed, but it never closed up. So the basin that formed, from what we can see, has mostly been filled with rhyolites and andesites, so felsic and intermediate volcanic rocks. So the problem is that if you do form an ocean basin, well, ocean basins, as we can quite clearly see here, the Granite-Rhyolite province is not a small area of crust. It's pretty large. And so in order to turn this into, continental crust, in order to turn this into something you can walk on, essentially you need to pretty much fill up this basin with material. And it would seem that the vast majority of material that filled up this basin was andesites and rhyolites, so volcanic rocks. So it would imply that whatever's happening in here produced vast quantities of intermediate and felsic volcanics. And the entire sequence then gets intruded by all these kind of mint-coloured stuff. That represents the granites and diorites that were feeding the volcanoes at the surface. So what are our two models to explain essentially how we managed to produce such huge quantities of volcanism? So there are two current models. The first one is mantle upwelling. So the suggestion is that underneath the Granite-Rhyolite province, a mantle plume comes up, and this mantle plume gets stuck at the base of the crust. And as we've already touched on in the past, it will begin to melt the crust, so thermal melting. So the mantle plume is very, very hot. The crust, comparatively speaking, is a lot colder, and so it will begin to melt the oceanic crust that it's stuck below. Now, the melting of this oceanic crust, of course, is not full melting, it's only partial melting. So the lower temperature minerals will melt first, so minerals that are typically rich in things like, potassium, sodium, silicon, aluminium. And that will produce magmas that have an approximately felsic to intermediate composition that can then go and feed volcanoes at the surface. So, that's one way that you could produce a relatively large amount of felsic and intermediate volcanics which could begin to fill up this basin. The other possibility is the process of delamination. So if you remember, below the continental and oceanic crust, there is a piece of mantle rock that is stuck to the bottom of both oceanic and continental crust. And that piece of mantle rock is solid. And if you remember, the piece of the crust and the mantle rock combined is referred to as the lithosphere. So in the process of delamination, what can happen is a portion of the mantle rock that's stuck onto the bottom of the crust can simply fall off. Now this is going to have very serious repercussions, because obviously if a bit of the mantle rock suddenly falls off from the base of the crust and starts sinking into the mantle, well, that means the amount of material pushing down on the mantle is suddenly reduced, and so obviously the pressure drops. And this is going to lead to the partial melting of the upper mantle and lower crust due to decompression melting. So once again, when you start melting the mantle, you're going to produce mafic magmas, quite hot magmas, and they're going to be rising up. They're going to get stuck at the base of the crust, and so they're going to start heating up the base of the crust, and they're going to start melting it, producing felsic and intermediate magma, which is then going to rise up to produce granites, get stuck in the crust, and it's going to feed felsic and intermediate volcanoes on the surface. The other thing that happens is the decompression melting will also affect not only the mantle, but also the lower portions of the crust, and once again that's going to encourage, through decompressional melting, that area of crust to melt, and that's going to cause the formation of, once again, felsic and intermediate volcanics, which will feed rhyolite and andesitic volcanoes on the surface. So both of these models essentially, to some degree, explain what we see. The one thing is that the Granite-Rhyolite province, as you can see, is a very, very large area. So a mantle upwelling, essentially like Hawaii or like Yellowstone, could in theory produce quite large quantities of rhyolitic and andesitic volcanics. However, it probably wouldn't be able to cover this large an area. So the most likely explanation is delamination. A piece of the mantle rock stuck to the bottom of the crust just fell off, and it caused decompressional melting of the underlying mantle and the lower portions of the crust, as the pressure was suddenly dropped as this piece of rock just fell off the bottom of the crust. So the Granite-Rhyolite province is best thought of as what's referred to as a large igneous province. That's a region of extended volcanic activity, something like the Deccan traps or maybe the Siberian traps of India or Russia, respectively. Okay, so we've been going for another 20 minutes, so once again, pause the presentation, get up, have a walk around, and come back in a couple of minutes, please. Okay everybody, so before we go any further, let's do today's code word. So the code word for this presentation is going to be uranium. I repeat, uranium as in the radioactive element. Okay, so now we're going to think about Mesoproterozoic orogeny, so that's the Grenville orogeny, and failed rifting. So Mesoproterozoic means middle Proterozoic. So between 1.3 and 1 billion years ago, an ocean basin along the eastern margin of Laurentia closed. So it's kind of the end of a Wilson cycle, not quite a perfect Wilson cycle, but it is the closure of an ocean basin. So once again, it's just like how the piece of oceanic crust between India and Asia subducted underneath Asia, and eventually India went and hit Asia. The same thing is happening as part of the Grenville orogeny. There's an ocean basin between Laurentia and this Grenvillian crust. That ocean basin gets destroyed, and eventually the Grenvillian continental crust hits the eastern and southern margin of Laurentia. So when this occurs, obviously we have a continent-continent collision along the eastern margin and in the Llano province, essentially marks the orogeny's southern limit. So as we can see, if we go back up here, we can see the impact occurs down here, essentially in central Texas, and the main portion of the impact occurs here along the eastern seaboard. So the collision marked the final stage of the accretion of Laurentia, and essentially Laurentia represents the core of what is now modern-day North America. So essentially at this point we formed the craton that's making the core of North America. So we now have around 75% of the North American landmass being present, and the additional 25% is going to be accreted along the western and southern margins during the Phanerozoic. So during this period, what's going to happen, as you can see here, we're going to have additional sedimentary rocks deposited here along the east coast and in the southern states. And we're going to have the formation of the Rockies is going to add significant quantities of material down the western coast here. So around 1.1 billion years ago, we begin to see tensional forces in the center of Laurentia leading to the formation of a U-shaped mid-continent rift. So as around 1.1 billion years ago, we actually have the start of a Wilson cycle. So we begin to see that essentially the eastern third of Laurentia is trying to rip itself off the central portion and western part of Laurentia. So we begin to see that this area undergoes extension, and we start seeing the formation of a mid-continental rift, a little bit like the modern East African Rift Valley. So the western limb of this rift extended through Minnesota, Iowa, Kansas, and the eastern limb extended through Michigan and Ohio. So the rift seems to have failed after around 20 million years. So the rift's trying to get going, but it seems to have died out after about 20 million years. So if the rift had actually been allowed to continue, the Rift Valley would have slowly extended, and Laurentia would have split up into two land masses, with the northeastern, northern and western states going one way, along with Canada, and the southern states forming another landmass. So we can kind of see it in this diagram here. So here's our pictures. You can see we have our, our original core of Laurentia. We have our Yavapai orogeny here. We have our Matzo-Labradorian orogeny here. We have the Granite-Rhyolite province here. We have the the Grenville orogenies here and here. And you can see we have this purple band coming up through here, forming this kind of horseshoe shape approximately. You can see this is a diagram from the textbook, and you can see it a bit clear. You can see it a bit more clearly there. And so, what we see along this band here is we see lots and lots of igneous rocks associated with rifting. So we see that the area during this time period has undergone extension. The crust has been stretched. We see the result of that. We see the formation of lots and lots of normal faults. We also then see the eruption of large quantities of basalt, which is being created by the melting of the underlying mantle as the pressure drops because the crust is being thinned. So we can see that what we have here is essentially the early stages of a Wilson cycle. And now if it had been allowed to continue, this limb would probably have continued to grow in a southwesterly direction. And this limb would have probably grown in a southeasterly direction. So you would have ended up with one landmass approximately this kind of size, moving off away from North America, whilst the eastern states, provinces of Canada, central and western states would have remained part of North America. Now, as I say though, this rift dies out after about 20 million years, and when that happens, essentially, the Rift Valley just fills up with sediment, and that's pretty much it. So, what about sedimentation during the Paleo and Neo-Proterozoic, so essentially throughout the Proterozoic? So once the Grenville orogeny was complete, Laurentia didn't undergo any more large-scale deformation until the Ordovician. So, there's a few 100 million years of essentially peace and quiet about to happen. So during the Proterozoic, we get three large fault-controlled basins developing, which began to fill with sediments. Now, to be clear, these basins are not rift valleys. Okay, they're not being made because the crust is under any kind of extension. The crust isn't being stretched. All you have is large-scale faulting in an area. This faulting creates a topographic low. That topographic low fills with water. It also fills with sediment. So the sediment that begins to fill this topographic low begins to push down on the faults, causing the faults to move. Because it pushes down on them, it causes essentially the faults to move downwards. That makes the basin slightly deeper, so it fills up with more sediment. That adds more weight, which pushes the faults down even further, and so on. So essentially it's a self-fulfilling cycle. Every time the basin gets a little bit deeper, that means there's room for more sediment in the basin. That pushes these faults down further, which means the basin gets deeper, which means there's more room for sediments, and so on. But the most important thing to remember is that these basins are not controlled by rifting, so they're not extensional, they are purely related to faulting. So the first Meso to Neoproterozoic, that's middle to late Proterozoic basin, extended through Montana, Idaho, and into Alberta in Canada. So this basin was filled with sandstones, shales, and stromatolite-bearing carbonates. So that's the sandstone, mudstone, carbonate sequence. So we know it had essentially a passive sedimentary sequence, a passive continental margin essentially. And the fact it has stromatolites in the sequence shows us the water depth could not have been that deep. So in terms of the sediments that were going into this basin, well, materials being eroded from the high ground created by the Trans-Hudson and other Proterozoic orogenies, and then that material is transported in a southwesterly direction into the basin. So if we go up here, so if you remember, this is the Trans-Hudson orogeny here, here, and here, essentially this Y-shaped feature, and the basin itself is going to open up around here, and so sediment's going to be eroded from the high ground here and deposited into the basin around here. So the second basin formed in the Great Lakes region, and that occurs during the Paleo and Mesozoic. That's the early to middle Proterozoic. And it consisted of, once again, a passive marginal sequence, so sandstones, mudstones, and carbonates. And these carbonates once again contain stromatolites, which tells us the water depth was not that deep. In the case of this basin, sediments were being sourced from the mountainous terrain produced by the Pinocchian orogeny. So if we come back up here, once again, so if you remember, the Pinocchian orogeny was this orogeny right here, where we had some little bits of continental crust and a few island arcs sticking onto the southern margin of the Superior Province, which is this large grey area here. And so this will have created a mountain range, and the erosion of this mountain range will have deposited sediment into a fault-controlled basin that formed around here in the Great Lakes region. The third basin comprises the Grand Canyon supergroup, and these Proterozoic sediments unconformably overlay the Archean basement. And these sediments were deposited between 1.2 billion years and 750 million years ago. So that's middle to late Proterozoic. So that's Meso to Neoproterozoic. Neo means late. Or should I say Neo means new, but it means the latest portion of the Proterozoic. So once again, these sediments consist of shallow water sediments, but also fluvial sandstones, shales, and dollostones. So once again, we have a sandstone, mudstone, carbonate sequence. So that's essentially a passive marine sequence. But we also have fluvial sandstones, and that shows us that the water depth was clearly quite low. It was quite shallow water. We also have the presence of stromatolites and carbonaceous algae. Once again, that tells us the water depth could not have been that deep. And the fact that we have these stromatolites, and especially the algae, show us that the water would have been, relatively warm and quite shallow, and probably quite clear as well. So, so each of these basins is forming essentially in a warm environment, and it's producing water which is relatively shallow, relatively warm, and relatively clear, and that allows for the formation of the carbonates, for the limestones. And the limestones that are forming contain stromatolites, which once again indicates the water depth must have been relatively shallow. So these are the approximate positions of these basins. So in the case of this Rocky Mountain Basin, we can see the materials being eroded from the Trans-Hudson orogeny around here, and moving in a southwesterly direction to fill the basin here. In the case of the Great Lakes Basin, we have the mountain range created by the Pinocchian orogeny, which is sitting around about here, which creates sediment that goes into the basin here. In the case of the Grand Canyon supergroup, the source of the sediment isn't quite as straightforward. So the Grand Canyon supergroup is forming somewhere down around here. And so it's probably coming from a mixture of Trans-Hudson orogeny here, and also several smaller orogenies that occurred in this area here. So, as I already touched on, the Proterozoic marks the time when we formed the first supercontinent. And we've already touched on, when the supercontinents formed. We've already mentioned the supercontinent Rodinia. And that essentially was formed as, that the formation of Rodinia is indicated by the Grenville orogeny. So, as we know, there have been several supercontinent cycles in Earth history. So essentially a supercontinent is defined as the joining of two or more continental masses, although most examples in the geologic record contain nearly all the continents with the exception of a few outlying islands. So at the moment we actually have two supercontinents. North America is connected to South America, that's one supercontinent, and obviously Europe is connected to Asia and Africa, that's another supercontinent. So we feel confident that given the accretion along continental margins and the presence of ophiolites, we know that plate tectonics as we know it was fully operational by the Paleoproterozoic. So essentially we understand that by the early Proterozoic things are working pretty much as we would have expected. So as we covered last lecture, there is some evidence for two supercontinents in the Archean. We called them Valbara and Cornland. But we also said that bearing in mind, how old the rocks are and how strongly deformed those rocks are, to prove definitively that those supercontinents existed is very, very difficult. So even if these supercontinents did form, they would have been very, very small, because the pieces of continental crust that would have been, making contact with each other would not have been that large. So geologists, however, feel pretty confident about the formation of a supercontinent called Nuna, which was present during the Paleoproterozoic, the early Proterozoic. We're 100% confident about the formation of a supercontinent called Rodinia between about 1.1 million years ago and 750 million years ago. So that's the middle Proterozoic, the Mesoproterozoic, to the late Proterozoic, the Neoproterozoic. And we then, right at the end of the Proterozoic, we have the formation of the supercontinent Panatea, and that's between 625 and 560 million years ago. So that forms in the very, very late Proterozoic, the Neoproterozoic. So these are our supercontinents here. So here we have Nuna down here. So we can see that from the evidence we have, it would seem that Nuna pretty much consisted of all of the available pieces of continental crust that were around at the time. Then we have Rodinia up here. Once again, we can see that the vast majority of the continents were part of Rodinia. We can see there were some outliers though, so it wasn't a complete supercontinent. And we can see this is Panatea over here. Once again, in the case of Panatea, we can see that the vast majority of the continental crust was incorporated into this supercontinent. So these are our three supercontinents that will form during the Proterozoic. And because the rocks we have from the Proterozoic are on the whole in pretty decent condition, we can say with relative certainty that yes, these three supercontinents did actually occur. So around 750 million years ago, Rodinia, this one here, broke up, but the pieces quickly coalesced again to form Panatea, this one here. So as you can see, 750 million years ago, this one breaks up. About 100 million years later, all these pieces of rock have now reformed, all these pieces of continental crust are reformed to form a new supercontinent. So Panatea began to fall to pieces around 550 million years ago during the very late Neoproterozoic. And this becomes very, very important when we start discussing the sudden appearance of large quantities of life during the early stages of the Cambrian. This breakup of Panatea is very, very helpful when it comes to the establishment of lots and lots of different species. So the continental collisions are certain as the continents are constantly migrating. But as already discussed, why do the continents actually break up? So one model predicts that maybe there's an insulating effect from really, really big pieces of continental crust. Essentially, that means the mantle underneath them gets very, very hot because it's very, very difficult to lose heat through these very, very thick pieces of continental crust. They act like a very, very heavy duvet, trapping heat. And so that means the mantle underneath these pieces of continental crust naturally becomes very, very warm. When it becomes warm, it becomes buoyant, it wants to rise, and so as it begins to want to rise, it starts to cause the continental crust to dome up, putting it under stress. It starts to stretch it. So there's also been suggestions that maybe it could be due to convection cells underneath the continental crust. One convection cell goes one way, one convection cell goes another way, and it starts trying to pull the continental crust in two different directions. That once again will begin to stress the continental crust and begin to want to pull it to pieces. And then, as we touched on as well when we were discussing Wilson cycles, there is the possibility that very, very large mantle plumes could also help to encourage the breakup of continents once again. This very, very hot ball of magma gets stuck beneath the continental crust, causing it to, this magma wants to rise. It causes the overlying continental crust to dome up. As it domes, it begins to enter extension, it begins to be stretched, and once again, that can lead to the formation of rifting. So there's a few reasons as to why, supercontinents might break up. Okay, well, we've been going for an hour. This is the place to stop this particular presentation. So please remember, today's code word was uranium, as in the radioactive element. So we're going to continue with the rest of this presentation in part 2. So everybody take care and keep your eye out for the next part of this presentation, please.